In this episode, we're going to introduce the very fundamental notion of linear maps. But before we talk about linear maps, it's of course necessary to pinpoint what exactly is a map, what exactly is a function. Well, a function is going to be a mapping from a set called domain to a set called codomain, where we're going to take each element little x of the domain as the input, and we're going to map it to exactly one element f of x in y. So for example, you can consider a function from R2 to R2 simply given by the translation x, y mapping to say x plus 3, y minus 2. So this is taking each point in R2 as an input and it's going to output something in R2. Another possible map is you can send xy, every xy to, for example, 0, 0. This is also going to be a valid function from R2 to R2. I guess something that has to be pointed out is that unless domain and codomain are very clear from context, you probably want to specify them. Because, for example, if you're going to just tell me that the function is xy being sent to x plus 3, y minus 2, then for all I know, this could be a map from, say, g mod 5 to g mod 5 2. You have to tell me that it's a function from R2 to R2 for me to actually understand what exactly this construct is. And another notation that you may see for just this mapping part is f of xy equals to x plus 3, y minus 2. This is exactly the same thing. One last thing that I want to say about functions is the concept of function composition. So if you have some function, say from x to y, and you have another function from y to z, then realize here phi is going to go from element of x to element of y, then psi is going from element of y to element of z. So we really here have an easy way to go from x to z right away. And how we're going to do so, and this is denoted psi composed with phi, is that we are first going to apply phi of x to go to y, and then to go to z, we're going to apply psi to this. And one notational thing that I wanted to remember here is that it goes backwards. You apply phi before you apply psi. Now let us talk about linear maps. So a linear map a priori is going to be a function from a vector space to another vector space. So here v and w are vector spaces over some field, but it's much more than just a function. It's a function that's going to respect vector addition and scalar multiplication. And we already talked about this briefly in episode 1, where we considered this particular example that I'm going to turn your attention to once again. So in episode 1, we were considering a function from R2 to R2. So here we have a map from R2 to R2 such that E1 out to be mapped to the vector 1, -1, and E2 should be mapped to the vector 2, 1. So here what's happening is that the E1, which is, if you remember, this standard vector 1, 0, so this is E1, and we want this vector to be mapped to 1, -1, which is this vector. So this is phi E1, and similarly E2 is being mapped to phi E2 right here. And we wanted this map to respect vector addition and scalar multiplication. So when it comes to vector addition, what we wanted is, like, for example, this vector, like E1 plus E2, to be mapped to phi E1 plus phi E2. So you want this blue vector to be mapped to this phi E1 plus phi E2. And we also wanted, when it comes to respecting the scalar multiplication, a vector like 3 times E1 to be mapped to 3 times phi E1. So more rigorously, we want phi of v plus v prime to be phi of v plus phi of v prime so that vector addition is respected. And similarly, we want phi of a times v to be a times phi of v. So now we have defined linear maps. Now another way of saying linear maps is linear transformation, and yet another way is to say vector space homomorphism. And due to this, we are going to denote by hom vw the set of all linear transformations from v to w. So this is going to be the set of all maps from v to w such that f is linear. Now something I want to turn your attention to is that for this map, we can specify where x, y is actually going to be sent to. So x, y of course is x times e1 plus y times e2. So by the linearity of this map, this has to be sent to x times 1, -1 plus y times 2, 1. Of course, the reason that this was possible in the first place was because for any vector in R2, we can get to that vector from E1 and E2 just using the vector space operations. Another way of saying that is that E1 and E2 spans R2. And we're going to talk about this concept more rigorously in the next video. But what this means is that for any vector in R2, it's going to be of the form x times e1 plus y times e2. But there's another thing about e1 and e2 that should be pointed out. So if you go back here, if we said e1 should be mapped to 1, negative 1, and instead of e2, let's say we said 2 times e1 has to be mapped to 2, 1, then we have a problem right off the bat. Because there's a linear relationship between e1 and 2 times e1. So if e1 is getting mapped to 1, negative 1, then 2 times e1 should have been mapped to 2, negative 2. So we see that it was also critical that there was no linear relationship whatsoever between E1 and E2. And as we're going to find out in the next video, this means E1 and E2 are linearly independent. So unlike E1 and 2 times E1, which had some linear relationship between them, E1 and E2 do not. Okay, I think that's enough of a preview for the next episode. Now I want to spend a little bit of time talking about the vector space R adjoint X. So the vector space R adjoint X is just the vector space of real polynomials. So remember, a polynomial is an expression of the form a0 plus a1x all the way to some a sub n x to the nth power, where here we're talking about the real polynomials, so the coefficients are going to be real. Now some linear transformations here from say R adjoint X to R adjoint X, you can consider a map that simply projects onto the, for example, the coefficient of x. So we can just project to a1. You should be able to easily check that this is in fact linear. And you can also consider the map that simply sends p of x to its derivative. If you know calculus, you should be able to also easily check that sending p of x to p prime of x should be a linear map. Let's spend a little bit of time talking about maps that are not linear. So what maps are not linear? So for example, you can consider the map from R to R just given by the absolute value of x function. And one easy way to see that this is not linear is that 1 is being sent to 1, minus 1 is being sent to 1 as well. So 1 plus minus 1, which is 0, should be sent to 2. But of course 0 is being sent to 0, so this is not a linear map. Yet another example you can consider is the one that we started with. So remember that this was a map simply given by xy being mapped to x plus 3, y minus 2. You may say, why is this not linear? You have lines. Well, the reason is that this map doesn't respect addition or scalar multiplication. For example, E1 is being sent to this vector. So E1, which is 1, 0, is being mapped to 4, negative 2, which is this vector. So 2 times E1, 2, 0, should really be mapped to 8, negative 4, but it's of course not. 2, 0 is actually being sent to 5, negative 2, which is this vector. And another way of seeing the problem here is that a linear map should really send the 0 vector to the 0 vector. And you may say, why is that the case? Well, to get some intuition over this, let us go back here. So this is just for the sake of gaining intuition. If you have this vector, that vector is being sent to this vector. And when we shorten this to this vector, now we are being sent to here, just because we are going to respect the linearity. And when it gets even shorter, then we're getting sent to here. And you should see, at least for R2, that when we map a 0 vector, then we should probably get to a 0 vector. And of course, this follows just from the axioms. So you can just check that, for example, phi of 0 times v should be 0 times phi of v. And 0 times a vector should be a 0 vector. And here you have phi of 0. So we see that a linear map should really send a 0 vector to a 0 vector. Another concept that I want to talk about in this video is the concept of a vector space isomorphism. And for this, we are going to consider two vector spaces. So let us once again consider the real vector space R adjoint X. So this was a vector space of real polynomials. And let's consider the vector space V of all real sequences that ends with repeating zeros. So what I mean by this is that we are going to have an infinite enumeration like 1, 2, 3, 2, so on, but we end with repeating zeros, so something like this. And it shouldn't be too hard to check that if you add component-wise and scale component-wise, then V should in fact be a vector space over R. But now I want you to realize that there is a very intimate connection between these two vector spaces. Namely, for example, let's consider a polynomial, a real polynomial, like 1 plus 5x minus 3x squared. And let us consider scaling this by 5. So when we're scaling this, then we're simply multiplying 5 component-wise onto the coefficients of the polynomial. So it's going to be like 5 plus 25x minus 15x squared. But now, in V, let us consider the sequence 1, 5, negative 3, and a bunch of zeros. And if you consider scaling this thing by 5, then we once again is going to get 5, 25, negative 15, then so on. I mean, to make the point even clearer, you can also think of this as plus 0x cubed plus 0x to the fourth and so on. And by this point, you may be asking, is there any difference between these two vector spaces if we only care about vector space operations? And the answer is, of course not. Of course not. These are the same. These are isomorphic. So iso meaning the same here. And a way of saying this using the language of linear maps is to realize that we have a linear map phi from R join x to V, in which we're just sending naturally the polynomial a0 plus a1x all the way to a sub n times x to the n to a0, a1, a2 all the way to a sub n, then zeros. And this phi is in fact much more than just being linear. So not only is phi linear, and that shouldn't be too hard to check, it also establishes one-to-one correspondence between the vector spaces in question. And what I mean by the one-to-one correspondence is that, just for the illustrative purpose, not to be rigorous at all, if you consider these to be the elements of R join x, then via phi we have this one-to-one correspondence that looks something like this. And two critical things that phi is satisfying here is that first, phi is injective. And injective simply means that we don't have a situation in which something in the codomain is being matched with more than one thing in the domain. In other words, if you have a phi of x being equal to phi of y, so if x and y are being mapped to the same thing, then they cannot be different, because then more than one thing is going to map to the same element. So in this case, we must have x equals to y. So phi has to be injective. And the second thing is that phi should be surjective, meaning that for anything in the codomain, we can actually get it as the output of the function. So in other words, for anything in the codomain, we can find something in the domain. So in this case, this is going to be a polynomial. There is a real polynomial such that p of x is being sent to V. And these two exactly mean that we have this nice one-to-one correspondence. And this is exactly the concept of isomorphism. So an isomorphism is when you have a homomorphism, and it also establishes this nice one-to-one correspondence. And I guess I should really add before we end that when something is injective and surjective, you say that that's bijective. Actually, there's one final remark that I want to make. Since phi is bijective here, you naturally have the concept of phi inverse. So this is when you're simply going backwards, following this one-to-one correspondence. So rather than going forward, now you're just going backwards. And of course, a natural question that arises is that if phi is an isomorphism, then is phi inverse linear? Then do we naturally get that the inverse is linear as well? And this actually turns out to be yes. And I invite you to prove this in one of the problems. Anyway, I hope you enjoyed learning about the concept of linear map, and I look forward to seeing you in the next episode.